talking. I just did one thing and she called out my name.
Right. So looking at this, it might be a little confusing. Let's read this first statement, okay? It says, since the second derivative is really the first derivative of f prime, which is the first derivative, the same relationships that exist between f of x and f prime of x must also exist between f prime and f double prime of x. So anytime all I'm doing is finding one derivative, the relationships that exist between them are the same as the ones that existed between the original function and its first derivative. So let's see if we remember what those relationships were. So what would we say was happening to the original function if we said the first derivative was positive?
Increasing.
So the original function had to be increasing, right? If the first derivative was negative, then what could we say about the original function? It was decreasing. Okay? So that was one derivative that we found, right? Okay, so let's think about this one over here. Let's say we're doing the first derivative and we're comparing it to the second derivative. Is that still one derivative that I found? Yeah, so if this derivative was positive, what did it mean about the previous one?
Decreasing.
It's also increasing. Right? If the second derivative was negative, what did it tell me about the previous derivative?
Decreasing.
It's decreasing. Okay, now the second derivative told me something else. It told me something about the original function. What did it tell me? The concavity, right? So it told me that this guy was concave up. And it also told me that here it was concave what?
Down.
Do we understand? This relationship here is the same because it's only what? One derivative. Okay? Do we know anything about the second derivative in this case? No. Got it? Sort of, maybe? Yes?
Yes.
Alright. Let's see if we can answer these questions then. Alright. If the second derivative is equal to 0 or undefined, what does that tell us about f of x?
Possible.
Very good. It has a what? Has a possible point of inflection at that particular value a, right? Okay. What would it tell me about the first derivative?
Possible relative max.
Very good, Eddie. So it has a potential relative max or what? Min. Is everybody okay with that, or are you confused? We can go into some further explanation. Are we okay or no?
Yeah.
Or you're just writing it down because I'm saying it?
Write it down.
Was good.
Are you sure?
So he doesn't get it.
He doesn't get it. Okay.
Don't be afraid to speak.
So how do I find potential maxes and mins?
Find critical numbers.
Critical numbers. How do I find critical numbers? Set the first derivative equal to 0 or find out where it's undefined, right? That'll give me my critical numbers, which are, whoa, my potential relative max or mins, right? So if we think about it, if let's say I don't have this guy and I'm starting here with the first derivative, and I find its first derivative, that will take me where? To the second derivative, right? So am I still doing kind of what I did here when I was comparing the original function to this guy? Yes, except now I'm not starting with f of x, I'm starting with what? F prime of x, and I'm doing this. So when I relate these two guys together, right, by me doing this is telling me where I have potential maxes and mins on that particular function. Yes?
Yes.
So if I had a first derivative graph, could I find the points of inflection quite quickly? Yes?
Yeah.
What would I have to look at on the first derivative graph to know where I have points of inflection? Max and mins, right? So if I come back over here, right? This is a first derivative graph. Where does it have maximums and minimums? Right there, right there, right there, right there, right there, right? Were those the possible points of inflections that we figured out over here? Yes. You understand? Did we have a point of inflection truly at -1, at 1, and at 3? Yeah, that's what we wrote down yesterday, right? After we did the sign analysis. We could have identified that really quickly if we would have known, right? That relationship. Anytime I want points of inflection and I'm given the first derivative graph, all I have to do is look at where it has what? Maximums or minimums. Boom. Those are my point of inflections. Let's go. Quick. Do you understand? Sort of? Alright, let's go on. If the second derivative is greater than 0, that means that it's what? No. That means that it's what? It's positive. That means that the original function is what? Concave up. So what would that mean about this guy, the first derivative? Is increasing. Beautiful. If the second derivative is less than 0, that means that the second derivative is what? Negative, meaning the original function would be concave. And the first derivative would be what? Cool? What happens if the second derivative changes from positive to negative? What can we say that the original function has? Okay, so the original function has a point of inflection, right? Because it's changing what? Concavity, right? If you wanted to be specific, as Robert was saying, it's changing from being concave what? Up to being concave? Down, right? But it's still changing concavity, and that's all that's necessary to have a point of inflection. Okay. So what would that mean happens over here?
Relative max.
Relative max? Okay, so that means that this guy is changing from increasing, right? To decreasing, right? Therefore causing it to have a relative what? Max. That's what we said, right? If this guy has a relative max, then there should be what here? A point of inflection. You understand? So we just said okay. Alright. What if it changes from negative to positive? What does the original function have? It doesn't matter? But now what does the first derivative have? Very good. Because he's changing from decreasing to increase. Got it? Papitas? Kindergarten stuff? No? It's a little challenging, yeah, it's kind of hard. Sometimes you gotta change your way of thinking to decide how things are related. Makes it easier if you kind of do this little table at the top, in case you ever get confused. Okay? This doesn't take too long to draw and come up with. Alright? We're gonna hold off on these guys down here. We're gonna come back to them right now. But since we're hot, let's keep it going. Okay. Turn it over from 1 through 17 and let's see if we can fill these in. See if you don't get pumped.
Oh, we do?
No.
So the first one says if the original function f of x is increasing, what can you tell me about the derivative? What does that imply about the derivative? Very good. What's another way of saying positive? Greater than 0, yeah, because I don't like to write stuff. What can we imply about the first derivative if the original function is decreasing?
It's less than 0.
Very good. This guy has to be less than 0, he has to be negative. If the original function has a relative or local min, what does that mean is happening with the first derivative?
It's changed to positive.
What does that mean? Changes from what? From negative to positive?
Yeah.
Very good. If the original function has a relative or local min, then what does the second derivative, what's happening there?
Positive to negative.
The second derivative changes from
Oh,
positive to
no.
negative.
At the point.
It has a point of inflection?
As a point of inflection.
If the original function has a minimum, how does the original graph have to look to have a minimum? It has to be concave up, right? So what does that mean about the second derivative? The second derivative is not concave up.
Possible point of inflection.
It's what? It's positive, right? It's greater than
Wow.
The only way my original function can have a minimum is if my function, the original function, is concave what?
Oh yeah, concave.
It's concave up. That's the only way I'm gonna have a minimum, right? So, what's gonna force it to be concave up is if the second derivative is what? Positive. Do you understand?
Yeah.
Yes? That was a tough one.
Yeah.
Okay, let's try the next one. If the original function has a relative maximum, then the first derivative is doing what?
Changing from positive to negative.
Changes from positive to negative. Okay. And if I have a maximum on my original function, that means my second derivative has to be what? Has to be negative? Why does this guy have to be negative? Because that'll force my original function to be concave down, therefore having a what? A maximum. And over here, this was forcing it to be concave up, therefore having a min. You understand? That was kind of, bless you, what we talked about yesterday when we were doing the second derivative test. Yes, using the second derivative to determine whether something has a relative max or min.
Yeah.
Good? Alright. If the original function is concave up, then that means the first derivative is what?
Yeah, it's increasing.
Increasing?
I would think so.
Yeah. Yeah. It's not, yeah.
Because the second derivative is positive.
The second derivative is positive.
So therefore it's
So if the
increasing.
second derivative is positive,
It must be
the
increasing.
first derivative has to be what?
Increasing.
Increasing. Very good. If the original function is concave down, then the first derivative is what?
Decreasing.
Is decreasing. If the original function is concave up, then the second derivative is what?
Positive.
Positive. If the original function is concave down, then the second derivative is
Negative.
negative. How do I know I have a point of inflection if I'm looking at the second derivative?
Change the sign.
It equals to 0 or undefined? Nope, those are
Change the
possible
sign.
points of
Change the
inflection.
sign.
Changes what? Signs. You spell it correct.
That's how I learned it.
Good. Alright, so now let's say the first derivative is increasing, that means the second derivative has to be what? Positive. If the first derivative is decreasing, then the second derivative is
Negative.
negative, because it's one derivative more, right? So this one's fun. If f prime of x is increasing, then the original function is what? Concave up. How do I know that? They wrote it on the front? Well, let's think about it relating to second derivative, right? So if this guy is increasing, that means the second derivative has to be what?
Positive.
Positive, and if the second derivative is positive, the original function is concave up, right? What's this one gonna be? Concave. Right, so tomorrow I'll give you the same exact handout again, without any notes, and let's see how you do. And we'll keep doing it over and over and over again until you get 100, okay? Sounds good? Repetition, okay? Practice makes what? Progress. Alright, so I want you to do these last two, give them a try, and let's see what you got. Right, so they're giving you some information and they want you to write two other statements. Okay? This represents the 20th derivative and this represents the 9th derivative. Okay, so that's the notation that you use when you're writing a derivative greater than 3. Right, so I don't want to put 4 little lines for the 4th derivative, right? Or 5 little lines or 20 little lines for the 20th derivative. We put the little number in parentheses like that. So let's see if you can come up with a statement, two statements,
Any statement?
any statement using that information, okay? While you do that, I'll pass out this handout. So if the 20th derivative is positive, what other two things must be true?